Alright, here we go. So today we'll cover a couple of things. One is take a look at reviewing a couple of practice problems, 33.11 and 13, both applications of the speed equation, and then we'll cover section 33.5 on shadows, and that'll be the last content that we'll cover in chapter 33. First off, before we get started, I had posed a question to you on the meaning of designations for radio stations. So one I suggested was an AM station 1390 WRSC, and the question was, what was the meaning of the 1390? Did anybody come up with that one? Well, let's see if you're correct. So the 1390 is a frequency, and that's what you're tuning when you're tuning a radio. This is frequency, and the 1390 means 1390 kilohertz. Or abbreviated like that. Now, many years ago, with old style radios from decades ago, and I'm sure your substitute today remembers this, Eric, the faceplate on old radios used to have those units. You'd see the AM band and it would say KHZ or kilohertz on it. Okay. Then the other question I posed was for an FM station, if you were tuning in to 95.3 FM station in the State College area, what's the meaning of the 95.3? Did anybody come up with that? It also is a frequency. Alright, so this one is also a frequency. But the frequency is in megahertz, not kilohertz. So that is done intentionally. All that is managed by the FCC in Washington. All the different broadcast bands are separated, so there's no overlap and interference, so that the AM band, the AM stations do not interfere with the FM stations. The same with the TV broadcasts. That would be at different kind of frequencies, and cell phone broadcasts would be at different frequencies, so so they don't get in the way of each other. So that's all very carefully managed. So let's take a look at those two practice problems. End of chapter on page 659. So the first one, 33.11, says that it takes 4.3 years for light from our nearest star to reach us. So the question posed is, how far, given that, how far away is that star in miles and in kilometers? So this is a two-part question. We'll do part A in miles. So this is an application of the speed equation. Speed is distance divided by time. You're asked in this case to solve for distance. So you can manipulate the equation. Distance is equal to speed times time. Now this is the English version, so we can use, now remember that the speed of light is a given, a constant. We're talking about in a vacuum in this case. So we'll use the English version of speed. $186,000 miles per second, and you're multiplying that times time, 4.3 years, and now you have to throw in a number of conversion factors. 365 days per year. 24 hours per day, and 1 day. See if I'm getting this right. And then and then 3,600 seconds per hour. I don't know if the camera can still pick up that part of the board. So your seconds units cancel out. Hours cancel out, the days cancel out, the years cancel out, and you're left with miles. And the answer given at the end of chapter is correct. I actually got 2.52 times 10 to the 13th. The book is reporting 2.53 times 10 to the 13th miles, so it's a long ways. All right, so speed equation plus a number of conversions. Right, the second part is expressing that distance in kilometers. So, like many problems, you can do it a number of ways. You could just take the answer that you got for part A and just apply a conversion to it, or you could redo the whole problem in metric. And the only thing you would have to do, if you want to do it, just do the whole problem over again in metric. All of the time conversion factors still apply. So distance equals speed times time. So the speed, of course, in metric is the 3 times 10 to the 8th meters per second. So you would just have to throw in a conversion to then express the meters in kilometers. So you have 1 kilometer for every 1,000 meters. And then again, all the 4.3 years, and then all the time conversions. And the answer in the textbook is correct. The 4.07 times 10 to the 13th kilometers. Now, as I mentioned before, that's the second part. As I mentioned before, you could just take your first answer and just apply a conversion. So the first answer was 2.52 times 10 to the 13th miles. And then you could look on the conversion table on the inside cover of the text, and that tells you there's 1 mile is equal to 1,609 meters. So you can just apply that conversion, convert the miles into meters and the meters into kilometers, and you'll end up in the same place. That's number 11. Now let's go on and talk about number 13, 33.13. A spacecraft sends a signal that requires 20 minutes to reach the Earth. How far away is the spacecraft from Earth? So So this one will be very similar to the problem we just did. So in this case, you're given time is equal to 20 minutes. We're talking about some kind of a radio signal which travels just like light. It travels at the speed of light. And you're asked to solve for the distance. So the answer in the book is in meters. The problem statement did not ask for certain units. So there's a variety of answers you could give, but we'll try to conform to the book answer. So speed is equal to distance divided by time. And once again, so speed So only one time conversion in this case is required. And the answer in the textbook is correct, the 3.6 times 10 to the 11th meters. Here's another one for you. How long does it take for a radio signal the moon with an answer expressed in seconds? So again, you'd use the speed equation. Speed is equal to distance divided by time. In this case, we're solving for time. So you again have to manipulate the equation. So distance divided by speed. So let's do this in English. We know the speed of light is 186,000 miles per second. But the question is, what's the distance from the Earth to the moon? I mean, it varies a little bit, but on average, what is it? Does anybody know it, or do any of you have a phone in your possession where you can do a quick internet search? Let me give you a minute for see if somebody can do a quick search, or if somebody can just suggest a distance that you already know. Well, to keep things going here, let me propose a distance for you. The generally accepted distance is 240,000 miles. If you divide that by the speed of light, 186,000 miles per second, go ahead and do that calculation and see how long it takes. The miles cancel out and you're left with seconds. That should give you about 1.29 seconds, so it's pretty quick. So, you know, like if you were talking on a telephone and there was a 1.29 second time delay between the two ends of the phone, that might cause you a little problem in terms of the delay, and the two people talking might stumble over each other maybe a little bit. But when back in the 1960s and early 70s, when we had astronauts on the moon, this was the speed of communication between the Earth and the moon at that time, and so the communication was very quick, and it was there wasn't much of a wait time, so it didn't get in the way. However, nowadays, when we have spacecraft up around Mars and rovers on Mars, you're talking a very long distance. So the time delay, I believe, we'd have to do the calculation, but I think the time delay is more like 15 minutes or so. So, for instance, if somebody in mission control on the Earth were sending instructions to one of the rovers to do something, it would take 15 minutes for the instruction to get there, and then once the rover did it and sent a signal back, it would take another 15 minutes to receive it. So things go a little bit slower in terms of that communication process. All right. Let's move on to the next section, 33.5, shadows, and this starts down at the bottom of page 649 and on to 650. So in discussing shadows, we're initially going to assume that we're talking about what's called a point source of light. In other words, the light is coming from a tiny point, not a large light source. And so it's like a little dot. And remember from our previous discussion about light rays move in straight lines, and in this case from a point source, the light rays are going to move out from the point source of light in all directions. Now this board is two-dimensional, so I can only show the light rays in 2 dimensions, but the light rays are also coming out towards you and away from you in all directions, 3-dimensionally. So then the question is, how are shadows formed? The way a shadow is formed is light is blocked by an opaque object. So what is the meaning of the word opaque? What would be a simple, like if you looked it up in a dictionary, what would the dictionary say? So opaque really means that light will not pass through, and that means no light. So an opaque object would completely block light. What term would be the opposite of opaque? Like for instance, the panes of glass over on the windows could be described as transparent, where all the light can pass through. Now there's a third term. What is a term that describes an object that lets some light through, but not enough that you can clearly see in a good definition of what's on the other side of the object? Does anybody remember that term? That would be called translucent. I think all of us have seen translucent objects. Probably the most common is you've seen, sometimes you'll be like in a commercial building and you'll be walking down a hallway and there'll be doors going into offices, and sometimes you'll see a door that has a pane of glass in it, but it's not transparent glass. It's translucent in that it's designed to let some light go through, but if you were walking down the hallway and looking in and looking at that translucent pane, you might see that there's something on the other side, but you couldn't get a real good clear sense of what's on the other side. You could see maybe that some objects are on the other side, and so. So those might be there for privacy or for whatever other reasons that transparent glass is not good. I'm going to stop the camera for just a minute, so hold on. All right, we're back. All right, so we talked about opaque, transparent, and translucent objects. So we're only dealing with opaque objects here in terms of formation of shadows. And the shadow that's formed by an opaque object is called an umbra, U-M-B-R-A. And that is also shown, if you can look at figure 33.11, at the bottom of page 650, you can see a good sketch of what that looks like. In that sketch, they're showing a source of light, which is a point, and there's an object that's blocking the light, and then the umbra is formed on a screen. Umbra sounds similar to the word umbrella, and I suppose you could say that an umbrella blocks the rain so it doesn't get you wet. So, similar type of concept. So now there will be some problem solving. So let's do recreate that sketch from the textbook, and then describe how you can do problem solving. So we have a point source of light. And you have light rays emanating in all directions from that point source of light. We are only concerned about these light rays. We're going to have some opaque object placed here that is going to be blocking the light rays. And then over here, we'll have what's called a screen, and on that screen a shadow will be formed on the screen. And that shadow is an umbra. Now let's label this sketch. So we're going to have one dimension. It's a lowercase d with a subscript O. That stands for the distance of the object from the point source of light. And then another dimension will be the lowercase h with the subscript O, which will be the height of that opaque object. We can also label the dimension, the vertical dimension of the shadow, h with a subscript s, so that is the height of the shadow. And then there's one more dimension. I'm going to need to erase this. Then we have lowercase d with a subscript s. That will be the distance of the shadow from the point source of light. Okay, I'm going to erase some of the definitions. Okay, so let's do a little geometry review. So we have two different triangles that we can identify. We have one triangle like this, small triangle, but then we also have a large triangle. Like this. So small triangle here, but overall you have a big triangle. And from geometry, what could you say about those two triangles? What kind of geometry term might be applied here? You probably had geometry in 9th grade. So it was a long time ago. Okay, so these two triangles are similar. Now, in a geometry sense, what does the word similar mean? So what you can see is that those two triangles are similar in shape, even though they're of different sizes. So they're proportional. Okay, so similar in shape, but different size. So because of that, we can set up an equation to do some problem solving. In other words, an example would be if you were given the distance of the object from the point source, if you knew the height of that opaque object, if you knew the distance of the screen from the point source of light, then you could do a calculation to predict how big or how tall the shadow would be. So in other words, you have four different dimensions, and if you were given any three, you could do a calculation of the fourth. So let's create the equation. So this equation is going to be a proportion, and a proportion, you create a proportion by setting two ratios equal to each other. So since the two triangles are similar, we can come up with this statement. The height of the object compared to the distance of the object from the point source is equal to the height of the shadow compared to the distance of the shadow from the point source. So let's do an example problem. Let's say you're given that the distance of the object from the point source, the opaque object, is 42 centimeters. And let's say we know that the distance of the screen, or the distance of the shadow from the point source, is 100 centimeters. And let's say that the height of the shadow is 30 centimeters. And what you're going to solve for is what is the height of the object that creates this 30 centimeter tall shadow given these other dimensions. So you're solving for the height of the object, so you can use algebra to manipulate the equation to put it in the proper form. So just a quick algebra review. So you want to get height of the object all by itself. So you could multiply both sides of the equation by distance of the object, and that cancels out. So you're left with the height of the object is equal to the height of the shadow times the distance of the object from the point source divided by the distance of the shadow from the point source. So let's rewrite this up here. So the height of the object is equal to the 30 centimeters times 42 centimeters divided by 100 centimeters, and that should give you, and so 2 of the centimeter units cancel out and you're left with centimeters, which is appropriate, and that'll be 12.6 centimeters. All right, so there's a quick example. I'm going to give you some practice problems, and so this is a model that you can follow. So let's take a look at this. If you look at, now go back and look at the sketch. Does that answer make any sense? It does. You can, if the sketch was drawn somewhat accurately, you would then already know before you did the calculation that the height of the object is going to be smaller than the height of the shadow. So 12.6 in this case does seem to make sense. So you should be able to recognize an answer that doesn't make sense. All right, one more topic in this section. So now we're towards the bottom of page 650 and then on to 651. What if the source of light is not a point source? What if it actually is larger than a point source? So if the object is large, then you will actually have a two-part shadow, and that is shown in a sketch at the top of page 651. You will have, so if the point source is large, the shadow will include an umbra and also a penumbra. And the penumbra is not as dark. So in other words, in the area of the penumbra, it is, some of the light is blocked, but not all of the light, because the light source itself has some physical size to it. And so you can see on page 651 in the sketch, some of the light is getting past the opaque object and forming a shadow that's not quite as dim as the umbra itself. Let's take a look at an example. If you could turn in your workbook to page 30, there's an example that you're probably familiar with. So this is on page 30 in the workbook. So here's an example. Now this is not to scale, obviously. Yes, the sun is much, much larger than the Earth, but this is not to scale. But this is good enough to kind of explain to you what's going on. So in this example, we're talking about a lunar eclipse. So the moon's going around the Earth, and then at some point the moon goes behind the Earth, and the light from the sun is blocked out, and the moon gets dark. But because the sun is not a point source, the sun has some physical size to it, then some of the light gets passed. So as a lunar eclipse develops, the moon first goes into the area of the penumbra, so it dims, and then it goes into the umbra and it gets really dark, and then it goes into the penumbra as it exits the umbra, so it's still dim but not quite as dim, and then it exits the penumbra. So if you see a lunar eclipse, you can recognize what's going on there. So a lot of the light gets blocked, but some of the light is able to get past. All right, so here are a couple of practice problems to work on. These will be end of chapter problems. Okay, this is page 659. Problems 15 and 16. So if you could work those two problems, and then we'll restart up a second video which will review those problems for you. It looks like you might need a conversion on the second problem. Alright, so have a go at that, and then we'll restart up in a little bit.